Hello everyone, I am Professor K. N. Maksore from Sanjoni College of Engineering, Kopargaon. In the last lecture, we have studied the basics of relative velocity and the acceleration method. In today's session, or in the today's lecture, we are going to solve the numerical based on the slider crank mechanism using relative velocity and the acceleration method. Relative velocity and the acceleration method, which is the graphical method, and using this, we have to find out the velocity and the acceleration of different points or the links in the mechanism. Again, while solving the numerical based on this relative velocity and the acceleration method, you have to solve with the three different steps. That first step is the configuration diagram, second step is the velocity diagram, and third, which is the final step, which is the acceleration diagram. If you fail to draw the correct configuration diagram, definitely you will lose the marks in the velocity and the acceleration diagram. If you fail to draw the correct velocity diagram, you will lose the marks in the acceleration diagram. That's why all these three steps are very important to get the good marks. Again, velocity and the acceleration analysis, which is the kinematic analysis, which plays very important role in the design and the performance evaluation of the machine or the mechanism. That's why this part is very important for the machine design and the performance evaluation. Now we'll start with our numerical. First of all, we'll read in this case you have to just read that problem statement carefully. Now our problem statement is this. The crank of a slider crank mechanism rotates clockwise at a constant speed of 300 rpm. The crank is 150 mm and the connecting rod is 600 mm long. Determine linear velocity and the acceleration of slider A. Second, angular velocity and the angular acceleration of connecting rod at a crank angle of 45 degrees from inner dead center position. In this case, this is the problem statement. The given data is the crank length is given to us, which is the 150 mm, connecting rod length, which is the 600 mm. Crank angle is of 45 degrees. Again, crank speed, which is of 300 rpm in the clockwise direction. Now in this case, rotation of that crank is very important, which plays very important role. Okay, now next what we want to find out? We want to find out the linear velocity and the acceleration of slider A or the piston A, which is the VA and the AA, which is the acceleration of slider A. Next we have to find out the angular velocity and the angular acceleration of connecting rod. That means omega C or omega AB and alpha AB that we have to find out. This is the data that we want to find out. Okay, next, in actual case, these are the data. In actual case, it is very difficult to draw this 150 mm and 600 mm on that A3 size sheet. That's why we have to take some scale. Here, for the simplicity, I have taken the 1:5 scale. That's why that OB, that way, which is the crank length, which becomes 30 mm, and AB is equal to 600 mm. AB, which is the connecting rod, that scale length becomes the 120 mm. Okay, one thumb rule is that while drawing this configuration diagram, velocity diagram, or the acceleration diagram, that initial length, that first link length, that first line that you are going to draw, that should be of 50 to 60 mm. 30, 40, 50, 60 mm. The 30 mm is again no problem. With the help of which is we can easily visualize your configuration diagram, velocity diagram, or the acceleration diagram. Now we will draw that configuration diagram. That configuration diagram is in the steps you can find. First of all, you have to draw the horizontal line. Next, I have drawn that crank at an angle of 45 degrees. Next, I have taken that 120 mm distance in compass. and I have marked that point A. Now in this case, A is the slider, AB is the connecting rod, and OB is the crank. That scale, here you have to mention the scale length. That composition diagram, which is also referred as a line diagram, you can again, which is also referred as a space diagram. Now your first step is over. Don't forget to mention the scale. In this case, scale is the 1:5. After drawing your configuration diagram, next task is to draw the velocity diagram. While drawing the velocity diagram, first of all you have to recognize which is your input link. Now in this case, crank is the input link. Sometimes it may be possible in the numerator, it may be possible that they will give you the displacement of the or velocity or displacement of the piston or velocity and the acceleration of piston. With the help of that, you have to find out the remaining data. Now in this case, that crank orientation, crank velocity is given to you. From this, you have to draw the velocity and the acceleration diagram. Now we'll start with the velocity diagram. In the velocity diagram, first of all, that crank speed is given to you, that you have to convert into the rad per second, which is of 2 pi into n. N is the 300 rpm, 160, which is the 31.42 rad per second. Okay. Next, here in this numerical, if you see this configuration diagram, there are the total 4 points O, B, A, X. We are drawing the velocity diagram, means we are just finding out the velocity of all these 4 points, as well as we are just finding out the velocity of all the links available in this mechanism. Point O and point X are having the zero velocity. These are the fixed points. That's why these are our frame of reference. Again, few conventions that we have to follow. In this case, while drawing the velocity diagram, I have just taken all the letters I have taken the all small letters. Again, while drawing the acceleration diagram, again that small letters with the suffix, I have used the small letters with the suffix 1, O1, B1, A1, X1. And in the velocity diagram, small o, small b, small a, and the small x. Now first we will just plot the fixed points, point A, O, and the point X, which are having the zero velocity. Okay. Point O and the X, which are having the zero velocity, zero. These are our frame of reference. Next, we will just draw one table. In this table, if you see, I just mark this link length. In this case, motion is given to this link OB through the prime mover. It may be of IC engine or the motor. Through this, motion is given to this link BA, and through this BA, motion is given to this slider. In the same sequence, you have to write down that link lengths. Again, you have to write down the velocity vectors of that velocity. In this case, point O is fixed, which is having the zero velocity. That's why for this link, you have to mention B with respect to O. Again, velocity of link AB is known to us. That means we can find out the velocity of point B. That velocity of point B we can find out. Okay. Now move to the next link, which is the AB. Now velocity of point AB is known to us. That's why here you have to mention VA with respect to B. A with respect to B. Again, move to the next link, which is the slider with reference to X. That sliding velocity is unknown. That's why, but X, velocity of point X is known. That's why here you have to consider the VA with respect to X. Now we'll start with the first link, which is the OB. For this link OB, its velocity vector is the B with respect to O, B with respect to O. Again, its magnitude is equal to, its velocity is equal to R into omega. R means its link length OB into its angular velocity. Okay. and that magnitude is of 474713 mm per second. That OB. Okay, one thing that you have to strictly consider when we are finding out this magnitude OB, here you have to consider the original length. Here don't take the scale length. Here you have to consider the original length, which is the 150 mm. Omega B with respect to O, which is of 31.42 into 50 into 150, which is the crank length. From this you will get this magnitude. Next, in the last lecture we have seen when any link rotates, its velocity is always perpendicular to the same link. That's why its velocity vector, which is perpendicular to the link OB, and this vector. What is significance of this vector? Which shows the direction. Here, one thumb rule or uh, one trick is that when we say the B with respect to O, you have to mention that vector OB bar, just opposite of this. B with respect to O, B bar. A with respect to B, B A bar. X, A with respect to X, X A bar, just like this. Just reverse this. Okay, from this you can find out the vector. Okay, now after getting this magnitude, it is very difficult to mark this distance on that sheet. For that again you have to take some scale. See, this scale is different. Your scale for the velocity diagram is different, will be different, and scale for the acceleration diagram will be different. Don't take the same scale. That means which is never possible. But don't try to take the same scale. These are the different, all are having the different magnitudes, and to draw that you have to take the different scales. Okay, now here I have taken the scale 1:100. That means that 4713, which becomes the 47.13. You can round off to the 47 mm. Okay. Now we'll start. Okay, again, now we have to draw. How to read this? You have to draw the velocity vector of link OB, which is the VB with respect to O, which starts from point O, which is perpendicular to OB. You have to draw one line which must be perpendicular to OB from point O, which ends at point B at a distance of 47.13 mm. You have to draw one line which must be perpendicular to OB at a 47.13 mm. Next, I will just draw one faint line which is perpendicular to OB. Next, on that line, I will mark distance 47.13. I will mark the distance 47.13. And at that distance I will mark the point B. And next I will mark that vector which is the phi B with respect to. Okay, again one important thing is that in this case, in your problem statement, it is mentioned that crank rotates in the clockwise direction. That's why this vector is towards this, that arrow which is towards this direction. That means this vector should be again in the same direction. If we take the moment, that moment should be in the clockwise direction. Okay. That this arrow is very important. If we fail to draw this vector, then we will definitely lose the marks in the velocity and the acceleration diagram. Your whole configuration of velocity diagram and the acceleration diagram gets changed. Okay. If you failed, and everything is based on this arrow. Okay. Now, after getting the point B, now we have to draw the second vector. Again, this is the link AB, which also rotates. Its velocity is again perpendicular to AB, which starts from point B, but its angular velocity is unknown. That we have to find out actually. That means 101%, which is the unknown. That's why we have to draw one line which is perpendicular to AB, which starts from point B and it ends at A, but this will not end because its magnitude is unknown. That's why you have to just draw one faint line. You have to just draw one faint line through the point V, which must be perpendicular to AB. You have to take this line perpendicular to AB and draw this line to the point B. Just draw one faint line. Next. Now move to the next link, which is the slider. For this slider, its velocity is VA with respect to x. Again, its magnitude is unknown. This is the linear velocity, which is the dx by dt. Its magnitude is unknown, that also again we have to find out. Again, its direction, which is the along the horizontal line. Along the horizontal line, this means you have to draw this slider or the line of action. This slider slides along the horizontal line. That's why you have to draw one horizontal line from point x. Now that x is known to us. From this point x, you have to draw one horizontal line, and these two lines intersects at common point, and that common point is the A. Yes. And just draw one horizontal line, and these two vectors intersects at common point, and that common point is A. Next, we'll mark these vectors VB with respect to A and VA with respect to x. And from this we will get our velocity diagram. After drawing this velocity diagram, next task is to do the analysis. In this analysis, you have to measure all these vectors. Now in this case, these vectors are unknown. That means BA. Now we got that BA. Measure this vector BA into the scaling factor. Measure this vector BA into the scaling factor. We will find out the velocity of A with respect to B. Again, this vector XA, which is in earlier it was unknown, but now we have find out. That's why that XA, measure this distance XA into the scaling factor, we will find out the velocity of slider A. Okay. Now that I have just found out that BA, I have just measured this BA and the XA. That BA is of 34 mm, XA is of 40 mm. Again, if you multiply by the scaling factor, this value becomes the 3400 mm per second, and so velocity of slider which becomes the 4000 mm per second. After getting these values, next task is to find out the angular velocities. If you look over here, I have written these formulas. For this OA, its velocity r into omega. This is again link. Its velocity is the again r into omega. R means its length and omega means its angular velocity, which is the omega b with respect to A into AB. Okay. Now we already measures this vector BA into the scaling factor. That means velocity of link AB is known to us. That velocity of link AB is known to us, which is the 3400. Now I want to find out the angular velocity of link AB. For that, you have to 3400 is equal to omega b with respect to A into AB. Okay, that is angular velocity of connecting rod. VAB, which is known to us, which is the 3400, is equal to omega b with respect to A into AB. From this, again AB is known to us. Again, I will again repeat you. Here you have to take the original length. Don't take the scale lengths. You have to just take the scale length to draw the configuration diagram. Otherwise, don't use that scale length anywhere in your velocity and the acceleration diagram. That AB is equal to 600 mm. From this, that 3400 divided by 600, you will find out the omega b with respect to A, which is the 5.66 rad per second. Again, velocity and the linear velocity or the angular velocity, which are the vector quantities, we require to magnitude as well as direction. In this case, we have find out the magnitude. Next task is to find out the direction. Okay. Now, how to give these arrows? Here, first vector is the OB bar. That means your vector, that arrow is moving from O to X. That's why this arrow is towards this direction. Second vector BA bar. That's why vector is starting from B to A. That's why this arrow is towards this direction. And next vector is the xa bar. That means vector starts from x to a. That's why xa bar. Now in this case, in the earlier condition, when that crank OA is rotates in the clockwise direction, for that we have taken this vector is towards this direction. If this vector is towards this direction, that means this link rotates in the clockwise direction. If you use the same theory principle for this to find out the angular velocity of direction of angular velocity of link AB. In this case, that vector is known to us, which is moving in the downward direction. I have just drawn the same link AB. Again, this is the vector VB with respect to A, which is in the downward direction. And when here we say that VA with respect to B, that means point A is rotating about point B. That means B is the center of rotation. And with that center of rotation, if we take this vector, that means this link is rotating in the anti-clockwise direction. This is rotating in the anti-clockwise direction or the counterclockwise. In this way, if we see this table, this is the slider A, VA with respect to x, which is the 4000 mm per second, which is the velocity of slider, or 4 meter per second, which is the velocity of slider, and omega B with respect to A, which is the 5.66 rad per second in the clockwise direction, which is the angular velocity of the connecting rod. In this way, we have to do the velocity analysis from your velocity diagram. Don't forget to measure these vectors OB, BA, XA. Here you will find that vectors. You have to measure these distances, and into the scaling factor, which is the 1:100. With this, you have to find out the actual velocities of these links. These are the with scaling factor, and these are the actual velocities. That these velocities we require in the acceleration diagram. Now we'll start with the acceleration diagram. In the acceleration, for that acceleration diagram, again we have the configuration diagram, velocity diagram, and now we'll start with the acceleration diagram. Now for the acceleration diagram, just like in the previous condition case, we have taken the that points O and X. Here you have to take the same points, but you have to just add suffix 1 O1 x1 O1 x1. Just don't get confused. I have just used the same notation, but to differentiate this velocity and the acceleration diagram, here you will find these are the OX. Here I have used the O1 x1. Next one is the, we'll draw one table that just like the velocity diagram, the table that this is the input link, next one is the AB, and next one is the slider. Again in this case also, these are remain same, but for the acceleration diagram, when any link rotates, when having the turning motion, it undergoes the two types of acceleration. One is the centripetal acceleration, and second one is the tangential acceleration. After locating O1 x1, now we'll draw that table. The table must consist of following columns. First one is the link, next one is the acceleration, next one is the magnitude, direction, vector, and the scale length. We'll write that table as per the motion transmits. Motion is given to this link OB, through OB motion is given to AB, and through this motion is given to slider, just like this. Again for each link, as we already mentioned in the last lecture, when any link rotates, it undergoes the two types of acceleration. One is the centripetal, second one is the tangential. That means again that AB is having some rotary motion, that means it is again having centripetal and tangential acceleration. For the slider, which is the only one component of acceleration, which is the linear acceleration, which is the dv by dt. Okay, now we'll start with the component wise, or that first one is the centripetal component of link OB, whose magnitude is known to us, which is either v square upon r or the r omega square. Its angular velocity is known to us, which is the 31.42, which is known to us, and its length is also known to us, which is the 150 mm. From this we can find out this value. That value is of which is of 1,48,082.46 mm per second square. Its magnitude is known to us. Direction along OB towards O, that vector which is parallel to OB. Along OB means which is parallel to OB and which is towards O. That means that vector is moving in the downward direction of this point O1. Next, that vector is the O1 B1 dash. To write down this, that trick is very simple. For OB, that velocity vector is the small OB, and in the acceleration diagram it becomes the O1 B1. But that O1 B1, which is divided into two vectors, two components. One is the centripetal, next one is the tangential. That's why what I have done, O1 B1 dash B1 dash B1. I will just add the point. That vector should be the O1 B1. That's why I have just added that point, which is the B1 dash. O1 B1 dash, which becomes the centripetal component. B1 dash B1, which becomes the tangential component. Okay. Now that vector is the O1 B1 dash, and that scale length, here I have taken the 1:4000 scale and scaling factor, which is the 4000. Now that length is of the 37.02, which is the scale length. Now how to read this? I want to locate the centripetal component of link OB, whose magnitude is known to us, which starts from point O1, which is along OB towards O. You have to draw one line which must be parallel to OB towards O, that means which is in the downward direction, and its length is of 37.02. You will find I have just drawn one line which is parallel to OB from the point O1, and at the 37.02 I have located this point, and that point is the B1 dash. Next one is the tangential acceleration. Again, this is a very important step. In this problem statement, it is mentioned that crank rotates in the clockwise direction with the 300 rpm, otherwise nothing is mentioned. If in your problem statement, if that crank rotates with the uniform speed, that means its angular acceleration becomes 0. But in this case nothing is mentioned, and angular acceleration of crank is also not given. That means you have the choice. You can consider that crank rotates with the uniform speed, hence angular acceleration is equal to 0. Hence in this case angular acceleration for this link is 0. That's why its component is 0. See, this is very important. You can assume this angular acceleration 0 for the input link only. You can't assume this data for the remaining links, because for the input link we give the input, that input in terms of from the prime mover. That prime mover may be the your pump, or your it may be of motor or the IC engine. For that, whether it rotates with the uniform speed or the varying speed, that data is known to us. But for the remaining link, which is that we can't predict, that we have to find out actually. Okay, next for the and we have located this point B1 and B1 dash. Now we'll move to the next link, which is the AB or BA. Its vector is the, now we have located this point B1. That means acceleration of point B is known to us. That means while finding out the acceleration of point A, it must be of AB with respect to A, with acceleration of A with respect to B. Acceleration of A with respect to B. Again, it is having the two components. One is the centripetal, second one is the tangential. Again it is having the formula which is the v square upon r. V square means its velocity, Vb with respect to a square upon AB. Its magnitude is this. You have to measure this vector into the scaling factor. For this scaling factor is 100. This distance AB into the scaling factor, we will find out the Vb with respect to a. The square of this divided by the original length, which is the 150 mm. I'll again repeat you, while finding out this magnitude, don't take the scale distances. The scale distances you have to use for the configuration diagram only. Don't use the scale distances in the acceleration diagram and the velocity diagram. Okay, now this magnitude is known to us. Again, its direction which is perpendicular to B, along AB towards B, and its vector is B1 A1 dash. See, now in this case for this AB, its velocity vector is the BA. That means in the acceleration it becomes the B1 A1. But that B1 A1 which is divided into two components. One is the centripetal, second one is the tangential. That's why I have divided B1 A1 dash and the A1 dash A1. Now we'll just move to the next step, which is the centripetal component. Its magnitude is known to us. How to read this? You have to draw one vector from point B1 which is along AB towards P, whose magnitude is the 4.82, and at the end, after marking this distance, we will get the point A1 dash, which is like this. You have to draw one line which must be parallel to this AB. For this parallel line, you have to draw one parallel line, and you have to mark that distance 4.82 mm, and we will get the point A1 dash. Okay. Now after getting that point A1 dash, you have to move to the tangential component. For this tangential component, its magnitude is known to us. Its magnitude is not known, which is the unknown. Its direction is known, which is perpendicular to AP. All these tangential components are perpendicular to the same link, which are the tangential acceleration, just like the tangential velocity in the earlier case. Now we'll draw one line which must be perpendicular to AB, which starts from the point A1 dash. From the A1 dash, we will draw one line which must be perpendicular to AB, and we'll just extend this line. You have to just extend this line because its magnitude is unknown. Now move to the next line, which is the slider A, which is the acceleration of point A with respect to x. Again, its magnitude is unknown, that we have to find out. This is the value we have to find out. Its direction, which is the along the horizontal line. This is the linear acceleration. That linear acceleration which is along the horizontal line, because this slider reciprocates and its velocity and the acceleration are along the horizontal line. Now we have drawn this line which is perpendicular to AB, and next we have drawn one line which is a horizontal line. Okay, and at the intersection we will get one common point, and that common point is the A1. We will get that point A1. Now you have to join these vectors. Your vectors will be like this: O1 B1 dash, O1 B1 dash, B1 dash B1. Okay. Next B1 dash A1 dash, B1 A1 dash, B1 A1 dash. That means that vector should be moved from B1 to A1 dash. That's why this arrow is towards this direction. Next A1 dash A1, A1 dash A1. That means you have to, your vector starts with the A1 dash and ends at the A1. That's why that vector should be like this. That arrow should be towards the A1. Next one is the slider, which is the x1 A1. That means that vector starts from the x and ends at the A1. Next, we have to draw the vectors, resultant vectors of all these links. Here we will find we have joined the OB. Here you have to join the O1 B1. Here I have joined the BA. That means here you have to join the B1 A1. This is the resultant vector of the acceleration of link AB. Here you have joined the BA. Here you have to join the B1 A1. Next, here we have joined Ax, that means here you have to join the A1 x1 or the O1, sorry, x1 A1, and from this, with this we will get your acceleration diagram. After getting this acceleration diagram, next task is to do the acceleration analysis. After finding out all this vector length, next task is to find out the solution. Solution, what we have to find out? We have to find out the angular velocity, angular acceleration of the connecting rod. For the angular acceleration, if you see this formulae, that angular acceleration term comes into the equation of the tangential component of the acceleration, which is the alpha r into alpha a with respect to b into ab. For this its total acceleration is known to us, which is the 1,03,000 mm per second square, divided by AB, which is the 600 mm. You will find out the alpha A with respect to B, which is the 171 rad per 166 rad per second square. Next, we want to find out the acceleration, direction of angular acceleration. Now in this case, its vector for the tangential component of acceleration, that vector which is in the upward direction, this vector a1 dash a1 which is in the upward direction. We have to move the same vector on the connecting rod. Again, that vector which is the a with respect to b, that means point A is rotating about point B, and that means B is the center of rotation. If this vector is in the upward direction, B is the center of rotation, that means this link which is in the link will be rotated in the clockwise direction. Again, with this, next one is the solution. The velocity of slider, which is the a with respect to x, you have to measure this distance into the scaling factor for the velocity diagram, which is the 100. With the help of this, we can find out the velocity of slider. Next one is the angular velocity of connecting rod. For this, you have to measure this vector vb with respect to a, divided by its into the scaling factor, divided by its original length, which is the 600 mm. We will find out the angular velocity, which is the 5.66. Next one is the acceleration of slider. For that, you have to measure this distance into the scaling factor, which is the 4000. With the help of this, you will find out this value, 1,17,000 mm per second square, which is the 117 meter per second square. Again, we have calculated the angular velocity of the connecting rod, which is the alpha a with respect to b. For that, we have measured this tangential component into its scaling factor, which is the 4000, divided by the original length, which is the 600 mm. From this value is the 171.66 rad per second square. This is the solution of this numerical. See, we have to take care of each and every step, which is the first one is the configuration diagram, next one is the velocity diagram, next one is the acceleration diagram. With the help of that velocity diagram, we have to draw the acceleration diagram. Every distance should be very precise, and with this precision, we will definitely get the good marks and we will definitely get the good answer. Thank you.